Greetings to the respected faculty. I am Lasya Mandapati from CSE AI&ML B section. My roll number is 24951A6686. Today, I'm here to present my project for the course Essentials of Problem Solving, or simply EPS. The project topic is removing duplicates, a core concept that deals with data redundancy. Today, I will walk you through how I tackle this approach or challenge using a space-optimized approach, directly manipulating pointers in linked lists. Let's start the journey. Abstract. In software development, redundancy in data structures like linked lists can severely impact efficiency and memory usage. This project focuses on removing duplicate nodes from an unsorted, singly linked list without using any extra space, a constraint that makes the task quite challenging. Using a brute force nested loop approach, we can scan each node against all subsequent nodes and remove duplicates in place by adjusting the pointers. The algorithm implemented in Python was tested against edge cases like fully duplicated lists and fully unique lists. While it is memory efficient, it has a quadratic time complexity which can be represented by O of n squared, making it best suited for small to moderate datasets. This project not only strengthens skills like pointer management and linked list operations, but also highlights the critical trade-off between memory and speed. Now, let us discuss the project overview. Handling large datasets efficiently is crucial today. Linked lists offer dynamic memory management, but can often suffer from redundancy in unsorted structures. This project provides a solution by removing duplicate nodes in place, meaning without any auxiliary data structures like arrays or hash maps. By adjusting the node pointers dynamically during traversal, we preserve the original insertion order while ensuring each element appears only once. This project is designed to handle linked lists up with up to 1 million nodes, pushing for deeper understanding of pointer manipulation and efficient iteration. It also lays the foundation for solving more complex data handling challenges in real-world applications like databases, system programming, and embedded systems. Moving on to the objectives of the project. The key objectives of this project are to understand and implement pointer-based traversal techniques for in-place node deletion, to preserve the relative order of nodes while removing duplicates, to operate under strict space constraints, achieving a space complexity of O of n, to validate the the algorithm across diverse text cases, including fully duplicated and fully unique lists, to reinforce problem-solving abilities under real-world constraints, balancing time and memory usage. This exercise not only solves a practical computer science problem, but also strengthens core algorithmic thinking for tackling bigger software challenges. To successfully tackle this problem, several prerequisites were essential, like strong understanding of singly linked lists, the traversal, insertion, and deletion operations, expertise in pointer manipulation to dynamically modify links during traversal, familiarity with nested loops as comparisons involve checking each node against all following nodes, knowledge of time and space complexities, especially aiming for O of n squared time and O of 1 space. Finally, a problem-solving mindset that balances algorithmic correctness with system constraints. On the technical side, the project was developed in Python 3.0 using Visual Studio Code as the IDE, tested across numerous inputs for validation. The heart of the program is in the algorithm. This is a quote said by a famous person, so I guess it's true. It uses two pointers. As in, this program uses two pointers. The current pointer, it traverses each node one by one. The runner pointer, for each current node, checks the subsequent nodes for duplicates. If a duplicate is found, we bypass it by changing the next pointer. This direct pointer manipulation ensures no extra space is used. While simple and effective for small lists, the trade-off is of n squared time complexity, which becomes a bottleneck for very large datasets. The methodology for this project can be broken down into simple steps. Accept user input to form an unsorted linked list. Invoke the remove duplicates function where in-place detection occurs using the two-pointer technique. Traverse and display the final linked list after all duplicates are removed. Validate by comparing the output with the expected results manually. Special focus was placed on pointer efficiency, simplicity, and memory conservation. The technology stack used includes Python 3.0, VS Code, and manual testing through extensive test cases. This is the code running on ideally. Let us discuss the project workflow. The project workflow is highly systematic. Start by accepting user inputs and building the linked list dynamically, applying the in-place duplicate removal using the nested pointer logic. Finally, traverse and print the updated linked list to verify results. Manual testing using varied data, including all duplicates, all uniques, and mixed sets, ensures the reliability and robustness of the code. This is the continuation of the code. Let us also discuss the technologies used. The technologies and tools used in this project are carefully selected for simplicity and effectiveness. Programming language Python 3.1, 3.10, chosen for its readability and strong support for dynamic memory operations. IDE, the Visual Studio Code, providing an efficient environment for writing, testing, and debugging. And the key concepts, which include linked list traversal, pointer manipulation, and nested looping, as we discussed before. And finally, for testing, manual test cases focused on validating functionality using various input scenarios. These choices ensure focus remains on the fundamental programming skills without unnecessary dependencies. Now, let us look at the results. The algorithm consistently removed duplicates and preserved the insertion order in all the tested cases. Some examples include input of 3532528, which gave an expected output of 3528. Next, this next input is all duplicates, which is 511111, which also gave an expected output of 1. Even with linked lists containing up to 100,000 nodes, the solution maintained correctness, although naturally slower due to its quadratic time complexity. Overall, the project validates pointer-based duplicate removal as an effective strategy for small and moderate-sized databases. The system output, as you can see here, the input was 12324 and gave an output of 1234. Let us discuss the system output in a little more detail. The system outputs were carefully documented to validate the program. Examples show that duplicates are correctly eliminated and the original order is preserved after applying the remove duplicates function. While execution slows down with large lists, the core requirement of zero additional memory usage was successfully met in all scenarios. The discussion section highlights important observations, which include strengths. Strengths include no additional space, usage, preservation of list order, simple and robust logic. Weaknesses are mainly tied to execution time. O of n square becomes a limiting factor with very large datasets. The trade-off is clear. We prioritize memory efficiency over speed. Possible improvements include introducing dynamic switching between algorithms based on list size or even parallel processing for large datasets. Applications are widespread, especially in embedded systems, mobile devices, and resource-limited environments, where memory optimization is crucial. To conclude, this project successfully addresses the problem of duplicate removal in unsorted, singly linked lists without extra space. Despite the O of n squared time complexity, it provides a highly memory efficient solution ideal for constrained environments. Future scopes include enhancements like using hash sets to achieve O of n time where memory permits, employing parallel processing for faster duplicate detection, extending the logic to doubly or circular linked lists, adapting it for machine learning pre-processing and back-end deduplication systems. This project thus builds a strong foundation in handling real-world data structure problems under practical constraints. The key references for this project includes classic computer science textbooks and algorithms guides such as the Corman Th. Lazarson C. Rivset R. L. and Stein C. The Introduction to Algorithms from the MIT Press, The Art of Programming, and Data Structures and Problem Solving using Python. These resources ensured the approach was robust, scientifically grounded, and aligned with the best programming practices. Thank you all for your attention and interest. I hope this session provided useful insights into memory management, memory efficient data structure management. Thank you.